Okay, today we're going to talk about fuzzy measures and fuzzy integrals. And these are used to aggregate information. And so let's talk about fuzzy measures first. So just consider a set of sources. These could be sensors, they could be people, be questions in a survey. Let's say that there's n of them. So we have n sources. And now what a fuzzy measure does is it measures the worth of each information source. And so g is a function, it maps to 0, 1 for each information source and all the combinations of the information sources, hence the 2 to the x notation there. And so it's the worth of all possible subsets of the universe of discourse. Okay, so let's look at this. So there's properties of these fuzzy measures. First, the boundary properties. So the measure of the empty set has to be 0. So the worth of the empty set has to be 0. It's just intuitive. The worth of all the information sources taken together has to be 1. That is, it has the highest worth, which also makes sense because all of your sensors taken together should be the most information you can possibly get. Second, it has to be monotonic and non-decreasing. So consider A and B, where A is a subset of B, which is a subset of the universe. Then GA, which is the fuzzy measure of set A, has to be less than or equal to the fuzzy measure of B, which of course has to be less than or equal to 1. Okay, let's see an example here of what a fuzzy measure looks like for a group of sources. So let's say that we have 3 sources. We have x1, x2, and x3. These are the universe. So there's going to be a fuzzy measure value for each one of these. These are called the singletons. And also, so the G of singletons, or the fuzzy measure of the singletons, is also called the densities. This will come up later. So then we also have the combinations of these 3 sources. So we have the combination of x1 and x2. We have the combination of x1 and x3. And we have the combination of x2 and x3. And so there's also going to be an associated fuzzy measure for these sets. Then there's the overall combination of all the sources, x1, x2, and x3, which of course is just the universe. And then there's the fuzzy measure of the universe, which, as we know from property 1, is going to be 1. So recall we also have the fuzzy measure of the empty set here, 0. And so this whole collection of subsets of the universe and their associated fuzzy measures is called the lattice. So you'll hear that talked about quite a bit. So the first place that G can come from is just set by experts. So you can ask experts' opinions on You can start with the densities and then work up from there. And then the second place is you can set it by some function. And perhaps the most popular way of doing this is what's called the Sugeno lambda measure. So the Sugeno lambda measure sets the fuzzy measure of all the possible subsets of the universe. So let's say we have subset A and a subset B by combining measures from lower levels on the hierarchy. And so let's say we have A and B such that their intersection is the empty set. They don't share any members of their set. So then the Sugeno lambda measure of A union B, or if we combine those two sets, is the measure of A plus the measure of B plus lambda times the measure of A times the measure of B. And so the Sugeno lambda measure always starts with the densities and works up. If you recall, the densities are the measures of the singleton. Okay, so if we think about our last example, the lambda measure of x1 and x2 together is just going to be the measure of x1 plus the measure of x2, this is a lambda, plus lambda times the measure of x1 times the measure of x2. And so where does this parameter lambda come from? How do we get lambda? Well, if we think about it, we recall back that the measure of the universal set has to equal 1. Hence what we can do is go through a bunch of math, and I'm going to save you all that, and we can get to an equation such that we can solve for lambda such that the measure of the universal set does equal 1. So what the equation you have to solve is lambda plus 1 equals the product from I equal 1 to number of objects that you have of 1 plus lambda gi. Obviously this equation is going to have multiple roots, and so you select the root that is lambda greater than or equal to -1. So what is gi here? So gi is notation for the densities. So in this case it would be notation for the measure of the singleton xi. Okay, let's see an example of that. So let's say we have the densities g of x1 equals 0.2, g of x2 equals 0.3, g of x3 equals 0.1. So some expert has come along and said to you, the worth of information source 1 is about 0.2, the worth of information source of 2 is 0.3, and the worth of information source 3 is 0.1. So now we can use the lambda measure to figure out the worth of combinations of those information sources. So again, we solve that equation. And so just plug in some values. Okay, so what you see here is that we're going to end up with what's going to be a quadratic. And so if we go through all the math to figure out this quadratic, what we end up with is 0.006 lambda squared plus 0.11 lambda minus 0.4 equals 0. So we put this into our favorite root solver, whatever your favorite is, and we get the following roots. 3.109, just rounded, and negative 21.44. So we want the lambda that is greater than negative 1. And it can be proven that you always get one root, only one root that is greater than negative 1. And so here, we're going to cross off negative 21.44, and we're going to be left with lambda equal 3.109. Okay, so let's see how this works out. So if we want the worth of the information sources x1 and x2 together, we just take their densities, add them, put our value of lambda in, and multiply their densities, and what we get is 0.687. So this is the worth of information sources x1 and x2 together. We want the worth of information sources x1 and x3 together. Do the same operation, and what we get is 0.362. The worth of 2 and 3 together, we get 0.493. And if we were going to go through the math of this, let's say we wanted just to show that this actually works, the information, or the worth of the universe, we could take x1 and x2 and add x3 onto that. So in this case, let's do that. We got 0.687, which is the worth of x1 and x2. So we're adding x3 to that. So then we plus 0.1 plus 3.109, which is lambda, times 0.687 times 0.1. And what we find out is that we actually we get 1. So there's some interesting properties about the Sugeno lambda measure. So let's look at those. So if the sum I equal 1 to n of the densities equals 1, then lambda actually equals 0. What this ends up to actually be then is a probability measure. If the sum is less than 1, then lambda is greater than 0. And if the sum is greater than 1, then lambda is between negative 1 and 0. So there's also other measures too, and if you look around the literature, there's many measures. Another one that's also used, because it's actually very easy to use, is the decomposable measure. So this just sets the worth of a set is equal to the min of 1 and then the sum of the densities of the members of that set. So for all xi in A, where A is a subset of the universe. And so you can see what this does is it just adds up the densities until you get to 1 and then caps it. And so it's actually a very easy measure to use, because you don't have to solve that big a quadratic equation, you don't have to root solver, you just simply add numbers. Okay, what can we do with this measure? We have a way of measuring the worth of information sources. Now we want to tie in the actual information that's coming from those sources. And the way that we do that is with the fuzzy integral. And what the fuzzy integral really just is a weighted average of evidence. Where the average in this case, it's going to be a fuzzy average. So let's say that we have some function h, and it takes the universe of discourse and it maps it to 0, 1. So what this really is that h is the answer to some question. So it's the support of a question. H is the support of a question. So in this case, maybe the question is, how good was the restaurant? Then each member of the universe is people, and they're giving a number between 0 and 1 as how good the restaurant is, where 0 is really bad and 1 is really great. So in some cases, people actually do work with a mapping of the universe of discourse to the real number line. And this does work with the Choquet integral that I'm going to present in just a few seconds here, but it doesn't work well with the Sugeno integral, and so we're going to stick with the 0, 1 mapping that you see here. So we're just going to assume that these are fuzzy memberships in the support of an answer of a question. Okay, so the first one, which I just mentioned, is the Sugeno fuzzy integral. So the Sugeno fuzzy integral, we're going to notate this by an integral sign with the sub s, takes the support of the question and the fuzzy measure g and it combines them together with unions and intersections. So we have one big union, and then we have an intersection. So okay, so what is this pi I and this a sub I? Well, in order to do this, first you actually have to order the set. And so what this assumes is that you've taken h and you've permutated it through some permutation indices I, such that h of x pi 1 is greater than or equal to h of x pi 2 for all your sources of information. Oops, this is n. So what this says is that you're just permutating such that the first source of information has the greatest support of the question down to the last source of information, which has the least support of the question. So you start with the people that like the restaurant and you end with the people that don't like the restaurant. And thus, the set A of I is just the reordered information sources. So what we have here is we're combining the sets of information together such that the worth of each set of information is going to be the worth of combinations of those information. So the first set of information that you consider here, so if I equals 1, you're actually combining the support of the question, h x pi 1, min with g a1, and so a1 is just going to be the first source of information taken by itself. So g a1 actually equals g of x pi 1. So it's actually the density of whatever this information source ends up to be according to this permutation. The second term, GA2, is going to be the worth of the first information source taken together with the second information source. So as you can see, what you're doing is you're building up the aggregation using the combinations of the information against this permutation. So the Choquet integral is similar to the Sugeno integral. However, rather than using mins and maxes, it uses sums and subtractions. So it's notated very similarly. So what we have here, sometimes you'll see it notated like this too, with the C sub g and the argument h. So you have the sum from I equal 1 to n, the support of the question from the ith information source, times the worth of the combination of the sources up to source I minus the worth of the combination of sources up to I minus 1. And so what this is saying is that you're adding the support of the question for the additional worth that source provides from the I minus 1 source to the ith source. So again, what this really represents here, this term, is the additional worth of the pi sub ith information source in answering the question. Okay, let's see some examples of those. Alright, so let's go back to the example that we had with 3 information sources, x1, x2, and x3. And if you recall, we had come up with a measure for those sources. So the worth of information source 1 was 0.2, the worth of information source 2 was 0.3, and then the worth of information source 3 was 0.1. And then we'd also use the Sugeno lambda measure to find out the worth of information sources x1 and x2 together, which was 0.687. The worth of information sources x1 and x3 together, which was 0.362. And then the worth of information sources x2 and x3 together, which is 0.493. And we know that the worth of all the information sources is 1. Okay, so now let's put some values on the question. So let's say that each of these sources are people, and these people were asked to say question, what is the quality of McDonald's? And so we get these worths because 0.3, information source 2, they eat at McDonald's a few times a week, so they're going to know what the quality of the food is. Information source 1, they eat at McDonald's, say, once a week, and let's say information source 3, they eat at McDonald's every now and then, maybe when they're just on a road trip. So thus, we're going to take the answer from information source 2 to be the highest worth in answering this question is, what is the quality of McDonald's? And this is a contrived example, but it doesn't work. So information source 1 says the quality of McDonald's is 0.3. Information source 2, they say that the quality of McDonald's is 0.1. So they eat there all the time, but maybe it's just because it's right next to work. And information source 3, they say the quality of McDonald's is 1. Man, they love McDonald's, but they realize it's terrible for them, and so they only go when they're on a road trip. So now let's see how these two integrals combine these sources together to get an overall measure of the quality of McDonald's, or the support of the question is what is the quality of McDonald's? Okay, so the Sugeno first. Okay, so the Sugeno is, we have the max, oops, this is 3, of h, I'm just going to notate this as pi I, and g a sub I. And so, if you recall, the first thing we have to do is order these sources. And so, this is going to be hx3 is greater than or equal to hx2. x1 is greater than or equal to h x2. So pi 1 equals 3, pi 2 equals 1, and pi 3 equals 2, just for those reordering indices. Thus, a1 equals x3, a2 equals x1 and x3, and then a3 is just everything. Okay, so now let's see these terms. So if we do the first term, we're going to have the max of a whole bunch of terms. So we got 1 min with the worth of x3. So the worth of x3 is 0.1. And then we have h pi 2, which h pi 2 is hx1. So we have 0.3 min with the worth of x1 and x3 together, which we look up here. We see it's 0.362. 0.362. And then we have 0.1 min with the worth of everything together, which is, of course, 1. And so overall, this is the max of 1 min with 0.1, which is just 0.1, 0.3 min with 0.362, which is just 0.3, and then 0.1 min with 1, which is 0.1. And so overall, our answer is 0.3. This is quality of McDonald's. I make no claims that this is the actual quality of McDonald's, just for example purposes. Okay, so now let's see. Okay, let's do the Choquet integral on this example. So Choquet. Oops. Equals the sum from I from 1 to 3 h pi I times GAI minus GAI minus 1. Note that GA0 is just defined as 0, because A0 is really the empty set. Okay, so let's put some values on this. So we have h pi 1 is 1, and we're going to multiply this by GAI, which is just the worth of information source 1, which is, worth of information source 3, which is 0.1 minus 0, plus the support of the answer number 2, pi 2, which is source 1, times GAI, which in this case, GAI2 is x1 and x3 together. So we have 0.362 minus 0.1, because this is GAI minus 1, is GA1, plus 0.1 times the information, all the information sources together, which is of course 1 minus 0.362. And so if we do the math here, we have 1 times 0.1 plus 0.3 times 0.262 plus 0.1 times 0.638. And we get a final answer of 0.262. Okay, so now you can see the difference here between Sugeno and the Choquet. They both return very similar results, just in different ways.